interesting to see how this event works. I've never actually been myself participating, so maybe I should do that in the future. Good, but let's start. And let's start with a question. Who is Elaine Herzberg? What did she do? She did something unusual. Anyone willing to guess? Let's make it a murder mystery. Who killed Elaine Herzberg?
Autonomous system.
Yes.
Oh, okay, great. No, great, sorry. No.
So he has the sort of a bit questionable honor of being the first person in the world killed by an autonomous car. And probably, I guess unfortunately, she's probably not the last person killed by an autonomous car, if I'm guessing it right. And her story goes somehow that the sensors of the car worked in a way correctly, and they were able to detect her, but then the decision-making system in the car sort of failed to detect her, they failed to classify her correctly, and then failed to make the right decision. So that's what can happen if something goes wrong with the AI. And there's other cases where things kind of go wrong with AI. So there's the investment decision case that was sort of a data analysis kind of case, huge sort of financial loss because of a bug in a software. The second one is really not maybe AI as such, but it's an example how software can be really fatal. So that was maybe 25 years ago already. The first case when it was somehow confirmed that software had killed multiple persons, maybe 5 persons were killed because they got far too much radiation from this device, and so on. And then the more modern things, what are there very much on the discussion with the AI, is these bias things and so on that can lead into something very problematic situations if it treats the different genders, races, and that kind of things in a different way. And the point why all this is leading is that somehow it's important not only to develop good models to do things, but it's important also to understand the engineering side of the AI applications to make sure that we would be able to avoid these kind of problems. And especially when things go to the real world, from the laboratories to the real world, then things start to look a bit different. And interestingly, there hasn't been that much work actually on this area. So what this, I guess the Google guys said a couple of years ago is that somehow there's a lot of work about software testing, there's a lot of work about machine learning, but very little work of the kind of intersection of those two things. I think it's now changing a bit. Somehow in the past 1 or 2 years, it seems there starts to be a lot of publications now about all kinds of ways to test deep learning algorithms and that kind of things. So it's getting better, but I think there's still a big number of work to be done. And one way to look at it is this kind of chart, which sort of shows for the classical software the cost division of the different phases of software development. It's a bit old, and the reason why it's a bit old is that nowadays it's not so easy to classify it anymore so clearly, because back then we had the waterfall models and the different phases were kind of clearly divided. Now with these agile processes, it's not as clear, but maybe somehow it's indicative, I guess, of the today's situation as well. And what we can learn from here is that the development is just sort of a small part of the big pie, roughly the same size as testing, and then the maintenance, the life, is the biggest part of the life cycle cost of the whole thing. And now a lot of the AI research is doing sort of very good and interesting work somehow here, how we do new models, new ways to do the core things. But if we want to make this AI really to work in real life, then we start to think about this. We need to start to think about the maintenance, which might also include all kinds of things like the electricity consumption of these things in the long run and the cloud fees of the system and such things. I don't know if anyone has tried to do anything like this for the AI software to understand that what are the costs for that, but I suppose it's maybe a bit too early also for that. Because this is another quite interesting chart. Because even if there's a lot of talk about AI, somehow it's only 4% of companies who say that they have really deployed something with AI. So it's a very small number. And my kind of hypothesis is that once this starts to grow, then the issues of how we should test them, how we should maintain them, how we should debug them, and so on, start to be kind of far more important than what they are today. And this is maybe the reason why I think this is sort of an interesting area to do research, because it has sort of real-life relevance, and it maybe has potential to become really important and big. And why is it then difficult? So we have done software engineering for the past 50 years, 70 years, and learned a lot about that. But why things do become different with the AI? And with AI, I actually mean about machine learning mostly, and within machine learning, I maybe mostly mean about neural networks. But so what makes things difficult? So this is the first thing, that somehow the AI doesn't always give you the right result. So you get something like 97% accuracy of detecting cats, or whatever you are doing. And the classical software engineering kind of starts from typically the assumption that you have a function and it's always doing the right thing. It's always giving you the kind of the right answer. And then you compare it. But here you start from the premise that you don't always get the correct answer. So how do you live with these statistical results? In cases where you are targeting advertisements, it's kind of pretty okay, as long as you are good enough. But in cases where it's sort of more serious decisions, it's maybe not good. Or it's not obvious how you deal with those cases when you don't get perfect answers. The other thing is this one, what is called oracle problem in the software engineering literature. And it's that we don't know the right answer. So in the reinforcement learning, Google AlphaGo trying to play the game of Go better than anyone else, you just know that it should play better. It should make good moves. But you can't really go and check that. Was this the right move? So, and this is a bit classical problem in that respect, that if you look at optimizations and that kind of things, you typically face the same problem there. So you know that you want the best possible answer for the traveling salesman problem, but you don't know what is the best answer, because that's why you are trying to optimize it. Then we have this case where we have problems of defining what is the right answer, which sort of links this testing quite a lot also to this discussion of AI ethics. So what should the software do? And who should decide what it should do? And who should then check that it's really doing? If we commonly agree that it should, for example, do this one, or whatever we want to say, how do we then ensure that all the cars on the market would do that? We can't sort of crash test all of them. We have to have some other ways to do that. And this whole business is sort of a bit of a block for a lot of these commercialization efforts of the AI systems. we have been discussing a lot with the medical companies, and they have the problem that if they start putting machine learning to their products, they can't sell them anymore, because then they don't get the certificate for the product. And one of the reasons why they don't get the certificate is that the authorities who give the certificates don't have a clue how they would test them and give the certificates. So that's the sort of different levels of the issue in a way, part for the developer side, part for the kind of regulator side, and so on. And also there's, of course, a lot of this societal discussion needed in a way that what is the right thing to do in different cases. And then there is this case that if, so far I guess the examples have been that everything goes as planned and everybody is nice. But then we always have these nasty guys who want to do something bad. And I guess many of you know about these adversarial inputs, that somehow you have a picture detection algorithm which is able to detect that it's a panda with not very high confidence. Then the nasty guy looks at the code, looks at the model used, and designs this kind of thing that looks like noise, sums it up to the picture. You get this picture, which to your eyes should look rather similar to the left-hand side picture. And now the image detection system is relatively confident that it's a gibbon. So you can sort of cheat if you want quite badly. And for the pandas, it's not so bad, but in these kind of cases, it starts to be rather bad. That by carefully adjusting some of these stickers to the stop sign, you can fool the system to think that it's a 45 speed limit. There's all kinds of ways how to maybe oppose that kind of attacks, and that's important, but somehow there seems to be all kinds of interesting ways to do them. A bit of a summary maybe of the challenges of this machine learning testing, in a way that the statistical results are there, how to live with that. We don't know the right answer, the oracle problem. And then the typical cases, I guess, are that those of you who have really worked on this, and I guess many of you are, you know that the programs don't crash. They just create strange results, and then you sort of scratch your head and try to figure out why the result was strange. So the bug and feature, it's not clear really that is it something that's now part of the problem, that it can't be done better, or is there something wrong? Could you do better by having a trivial bug fixed in somewhere of your code, or by having a better model, having better teaching data, having all kinds of things. So this is kind of the problem domain where we are, and why things are difficult for the machine learning models. And of course there's answers, and this is the kind of standard answer we have today, that you have these all kinds of statistical measures which sort of check how good your results are. And you have sort of the approaches how you divide your data to training sets, test sets, maybe the development sets, and then you get these different things. And then depending on your problem, your domain, sometimes true, false positives are a problem, sometimes false negatives are a problem, and so on. And this is, I guess, very well understood. But then where things start to be, but this doesn't cover everything. And then there's other ways, in a way, that are in the literature. There's a big number of different ways. The first one is just to start from the software engineering approaches. That let's take all the classical software engineering stuff, the code coverage, unit testing, those kind of things, and apply them. And yes, you can do that. It might be helpful. But the problem is that often in a machine learning case, the number of code lines is very small, and it's easy to get the code lines right, but still get the results wrong. So there's a limit, in a way, how these regular software engineering ways work. N-version testing means that you have multiple ways implemented for the same problem, and then you check if they give the same answer. That's nice, I guess, but it's quite a bit of effort to develop multiple solutions for the same thing. You can save effort by being clever in that respect, that you might compare the operation with an old version of the thing to the new version and that kind of things. So definitely, I guess, worth considering. Metamorphic testing seems to be getting increasingly hot topic. And what that means is that it works in those oracle problem cases where you don't know the right answer, but you know some kind of relationship between the answers. So if we take a typical example, you have the traveling salesman problem, where you want to find the shortest route to visit all the cities. So then if you add one new city to the problem, then of course the new route should be longer than the old one. So that's a typical example of the metamorphic testing. And they have created quite interesting, or they have been able to detect quite interesting problems. For example, in these car cases, by looking at this point cloud of the LiDAR data, the car produced by the car, and then adding a few more points there, has resulted into some of the previously detected cars or pedestrians disappearing, which doesn't sound too good. But that's nice, because that can be kind of done in a way, in a rather automated fashion. So that might be, I guess, an important direction to go. And then you have these ways which somehow try to look into the neural network. So you kind of have the white box or gray box ways of looking at the activations inside the neural network and trying to understand that, are these somehow reasonable, and in the training, have you sort of trained it sort of in a balanced way, and in the usage that does do the activations in the usage kind of statistically resemble the activations that you had in the training phase, and that kind of things. And then finally you have some of these theorem proving approaches which I'm not extremely familiar with, but they are based on some kind of SAT solver kind of things, where you try to create as tight border between the decision classes as possible. And by trying to create as tight border as possible, the idea is that then you eliminate the space for these adversarial attacks and that kind of things. And probably there's many more, but these are some of the ones that at least I have sort of encountered. So now we have been talking of a single machine learning model. But in reality, you need much more than the single machine learning model, which is there in the middle. And this is some Google numbers which say that the machine learning code is typically 5% of the total code of a production system. So you need quite many things around the machine learning. And then some of them perhaps are easy. Some of them may not be easy. And at least you have to pay attention how they sort of fit to this machine learning and so on. And where it gets really interesting is that if you have this, you typically have dependencies between the different modules in your software. So there's one module whose output goes as input to another module, and so on. And this is my sort of favorite case, that you have two machine learning models, and the output of that goes as input to the other one. So now you make this better. You improve this model. It gives better results from the local point of view. But this module has learned how to live with the bad results. So what happens now when this module starts to get different kind of results than what it used to get in the past? Would it need to retrain itself again? So the problem seems to be that whenever you change something, it's very, very sensitive to small changes everywhere, easily sort of spread to other parts of the system very rapidly, which is a bit kind of counter to these software engineering principles where everything should be extremely modular and the modules should be as independent as possible. Something, this is sort of an idea of how life changes, what kind of new tests you need. So not maybe going to the details, but there's plenty of things you would need to test in addition to the old-fashioned way you used to test. You would need to test your data, models, all kinds of things. And finally, one way how some people are approaching this is, I have understood, rather popular now in the Silicon Valley, that the companies are sort of doing this type of self-evaluations of their machine learning capabilities. And they have this sort of different criteria and different sort of levels where you are, and then you kind of just self-evaluate yourself and you realize that, okay, on this data test I'm at level 2, and on this some other test you are at some other level, and so on. And then you get some kind of numbers where you are. And then that can act as a basis for your future development of your competencies and of your company processes in a way how you are going to make it better. So that was the general story. And then I have something about what we have done. We haven't done too much, because as said, I started at the end of the last spring. So this is about the only thing we have completed so far here, which was sort of a student project. So the guys in the middle are the ones who actually did the thing. Tommy and me kind of were providing the ideas and helping with the supervision. And the thing we sort of did was a tool called DPEMU. And the idea there was to create this type of fault injector that artificially sort of creates faults to the data sets. And why would you do that? Is that then you can sort of see how your system or machine learning module or system works with that problematic data and see how it affects. And the idea is that it would then be able to answer these kind of questions that how sensitive your machine learning system is to different kind of faults in the data. And the faults in the data are common in that respect that, for example, if you have a sensor measuring some number, sensors have a thing called drift, that they over time start to systematically go wrong. They might just stop working. You don't get anything for a while, maybe because of some network problems. Maybe the temperature goes so low that the sensor stops working for a certain period of time and gives some kind of really strange numbers. There's all kinds of problems in the data, and then the question is how your system sort of tolerates them. That does it crash them if you have a real system? Then in the development phase, the question is that if you can choose between multiple machine learning models, is there some model which is more tolerant to these problems in the data than another one? And then within a model family, somehow then comes the hyperparameters architectures, that can you find some combination of those which is robust against the problems and so on. So the idea is that some kind of general purpose tool which would solve in a way many different problems depending on what is the point of view, what you are looking at. And it's based a bit on the idea of something called positive and negative testing. And what that means is that you have the system under test, what you are trying to test. And then the typical way for positive testing is that you want to check that the system works correctly with expected input. And that's typically the kind of test that is done a lot for all kinds of systems. what is not done so much because it's very resource consuming and complicated is this negative testing, that how do you make sure that it doesn't behave badly with strange inputs? Especially in this sort of computer security, ICT security area. They do a lot of this fuzzing, that they just generate arbitrary strange inputs and then they try to check that does it create some kind of strange behavior. The problem, of course, is that then the sort of the complement of the expected input is sort of huge space, and then how you cover that space is difficult. So the concept that our tool tries to do is that we don't just create all kinds of strange input, but we somehow try to generate some kind of typical faults. And the idea is that we have specific error models that create this type of typically faulty behavior that you see in these systems. And there's, I guess, prior literature, and if there's not, then we should maybe create the literature about what are the typical problems in different kinds of data sets coming from different data sources. So this is sort of a brief architecture, but maybe the left-hand side, those issues are what we sort of were doing there, is that you would be easily plug in your any model, any system to the framework we have created. You should be able to pick some of the existing fault models from the system. Okay, let's take this typical sensor problem, let's take this typical camera problems, and so on. Or you should be able to create your own error module, modeling the kind of errors that the system you are investigating should kind of generate. Then you can run it on your PC or in a cluster, and then you can visualize the results, and then you can kind of track back from the results to the error, to the kind of fault case that what was the thing that generated that. The idea is that it would be helpful in many ways. And how it would be helpful is this, what we did. So we sort of had a set of experimental use cases where we sort of tried how the system works. So they were not maybe very deeply scientific studies, but they were more like guidance for us in the development of the system to look what is needed. But they gave some quite interesting results. And I'm going to tell a bit more about the first and the last by showing these examples. And this is the first case. So unsupervised learning. So you have these MNIST handwritten digits, and you then just try to classify them. And we have ways to generate added noise to the thing, missing pixels, combination of added noise, missing pixels. And this is the kind of things that you would get. This is now sort of mixing pixels. So this is the probability. What is the probability for each pixel to be there? This is the original data, so everything is there. Then you have 10% probability that the pixel is white, and so on. And what we can see here, so first of all, each of these is clustering the different digits. And in this you see that, well, some of them are difficult to differentiate already. So 6 and 9 look kind of similar. And then there's this bunch here in the middle, which is also similar. And then when you start adding the probability that the pixels are missing, the things start to get fuzzier and fuzzier, and 40% of the pixels missing, it's kind of okay. Half of the pixels missing, you start to have more serious problems, and then of course here you are maybe not in a complete mess. And then what we looked at this was that we looked at 3 different classification algorithms. And the interesting thing maybe was that here we can see the case where the algorithm that is very strong in the sort of perfect case, the performance of that drops faster than the performance of the other algorithms who were not that good in the case. So then the question, I guess the application of this is that if we know that there's likely to be problems, then perhaps the most accurate algorithm is not always the best, but the most robust algorithm, or the algorithm that combines the robustness with the accuracy, might be the best. Another case where we did this object detection. So here the added rain, added snow, not I guess claiming that it would really rain on the thing, but there's some kind of things that cause this kind of effects in cameras. And here at least we see that the added rain kind of confuses the bounding box. That's far worse here than what it should be. And that's probably because the rain has this sort of vertical lines generated there. And the same observation in a way here, in a way, of the robustness of the algorithms, that the retina net, which originally came third, when you started to make the resolution of the picture worse, then the retina net started to do better than these two that were originally doing better. So again, sort of the same message, that the robustness is sort of interesting and important. So in conclusion, somehow, this is something we hope would be useful as a basis for something bigger. It's not perfect yet, but it's available as open source. So if anyone considers that something like this would be useful and helpful for their work, it's there. You can take it, you can give a try, you can go and extend it with your own error models, and so on. And of course, we would be extremely happy if something like that would happen. And finally, what's happening now? So we are looking for a postdoc or a PhD student. If anyone knows someone who would be interested of this area, then we have a position open. We are running a seminar on testing on AI this autumn. We have something like 10 students there. End of November, we have the seminar day. It would be very nice to have also external audience there. So if you are interested to see what the students have been able to do on this topic, then you are most welcome to participate. We have been waiting a long time for Business Finland to make up their mind about this ITEA proposal. It's a joint European project funded by Business Finland in Finland, and now the latest news is that they should decide it before Christmas. I hope they do. And yes, so I guess this whole area, how you should really do the industrial scale development of machine learning AI-based systems, is sort of a big and interesting topic for us. It's not just me, but it's also Tommi Mikkonen and others who are sort of looking at this. So I guess we would be very eager to learn from what kind of problems you have had or you are aware of, or problems that would be important to solve on this area. So if anyone knows anything, so all challenges are extremely welcome. And with that, I guess I'm done. So thank you.